Hello, and welcome to this lecture taking a look at scientific progress. And I'm going to take a fairly controversial standpoint and take a look at this from the perspective of the history of alchemy and how alchemy and the response to alchemy has continued to influence science in the 21st century. So to start out with, what is alchemy? So basically, it started out originally in ancient Greece, so roughly, 2,500 years ago, maybe a little bit more than that. But the ancient Greek philosophers basically identified fire, air, water, and earth as the four elements. Now, at about that time, the philosopher Aristotle, was active and putting his ideas out there. And even though fire, air, water, and earth are often referred to as the Aristotelian elements, Aristotle felt that there were actually four elements: were hot, cold, moist, and dry, which contributed to the concepts of the earthly elements, this fire, air, water, and earth. And so what we've got in using the ancient symbols for this, we've got fire here as an upward triangle. Fire represents Aristotle's hot and dry. The opposite of fire, kind of down here in the corner, is water. Water with a downward triangle is the opposite of fire. And so if fire is hot and dry, water is going to be cold and moist. We've got earth over here, the downward triangle with a horizontal line kind of near the bottom of the pit. This is going to represent cold and dry, and the opposite of earth is going to be air. Air is going to be an upward triangle with a crossbar horizontal line near the top. And again, opposite of earth, which we said was cold and dry, air is going to be hot and wet. Now, a lot of times, these four earthly elements would add an additional one, ether, sometimes called void, in other cultures, represents the heavens. Now, even though this is often attributed to ancient Greek philosophy, this was prevalent in many other cultures within the world, very prominently within India, in both the Hindu and the Buddhist cultures, as well as Japan, having the same basic ideas, although oftentimes they would replace air up here with wind rather than taking a look at it as air. And so what does this mean? We think about these four basic elements, fire, air, water, and earth, represented an understanding of the world for almost 2,000 years, until it was challenged by the views of modern chemistry and atomic structures. Now, recognize, 2,500 years ago, they didn't have the fancy equipment. They didn't have, our understanding built upon all of this scientific knowledge that's occurred in this period of time since then. So even though these four basic elements have been challenged, they still represent the physical states of matter. And this is represented on this slide, taking a look at the hydrologic cycle, taking a look at the kind of water cycle. And so we got water starting out here as a liquid. Water can evaporate, and basically water is going to convert into a vapor, basically move up into the air. So we can think about it moving into the air. So we've got the water, we've got the air, and then ultimately, as we've formed these clouds up here kind of in the top, not going to focus on the meteorological things that are occurring, but ultimately the water vapor in the air is going to come down as rain, or if it's really cold, it's going to come down in a solid form in the form of snow or ice. So in this situation, again, it makes sense, from the standpoint of what they understood about the world for them. The three states of matter: liquid down here in the water, air, taking a look at the water vapor, and then solid here. And then if we add in that fourth basic element, that element of fire, what we can see is that is going to be what converts between these different states. And so if you want to, make water from a solid, you take snow, you take ice, and you heat it up, and it's going to melt. And so fire helps in the conversion of the state from a solid to a liquid. It can also help in the state of going from a liquid to the air, so a liquid to a gas. You boil a pot of water, and over time you're going to have steam coming up as the water vapors move into the air. Now, going back from the air into the either the liquid or the solid, you're basically removing heat. You're moving the fire associated with it. And so that's the background that philosophers and people studying the world with the tools they had available for a number of years. But this gave rise to the concept of alchemy, and alchemy is described as a protoscience. Now, alchemy came into prominence in the 16th and 17th century, and it's described as a protoscience because it was basically kind of an unscientific field, kind of by definition, but it developed into a scientific field, which would eventually become the world of the realm of chemistry. So alchemy became chemistry. Now, in alchemy, and we've got the symbol for the philosopher's stone, famous in movies and books, but there is kind of a historical precedent for this philosopher's stone. Alchemists looked for a philosopher's stone. This was a mythical substance that had the ability to basically convert base elements like lead into gold through the process of transmutation or metamorphosis. And so there was this desire to convert one element or one material into a different material, what we now know using the ideas of atomic chemistry and our understanding of the true elements, again, with the science we have available to us today. We're looking at converting one element to a different element. And so, not really scientific at that point, but they were still at that precipice, at that start of moving into the scientific method. We've got famous scientist Robert Boyle, who's recognized as one of the founders of modern chemistry. He has gas laws named after him, looking at the properties of gases and temperature and volume and things like that. He started out as an alchemist and is recognized as a prominent early chemist. We got Isaac Newton, who again is recognized as a great physicist, came up with the laws of movement, came up with the laws of gravity, and so mathematically described what people were observing in the world around him. He started out as an alchemist as well. And so, we can sit here in the 21st century and, kind of laugh at the views of the alchemist. But, in reality, were they really wrong? If we take a look at this concept of transmutation to convert one metal into a different metal, it does occur. And that's something that we now understand that occurs kind of in nuclear reactions in the center of stars. And humanity is taking that one step further. We've done or not we, but scientists have done nuclear reactions using particle accelerators. And so an example of that, a very prominent example, is that in 1980, Nobel laureate Glenn Seaborg and others, and get my notes right, at the Lawrence Berkeley National Laboratory Particle Accelerator, basically took carbon and neon nuclei and using this particle accelerator, shot it kind of close to the speed of light into these foils of bismuth. Again, a metal, a material, bismuth is a material, foils of that, and was able to create small amounts of gold. And this is illustrated here kind of at the bottom. This is the abstract for the article that indicates that they were capable of doing transmutation. They were capable of doing what alchemists were searching for with the philosopher's stone. And Seaborg, not getting the Nobel Prize for proving alchemy, he got it in 1951 for creating plutonium. Basically, started out this field of transmutation at a atomic level, taking a look at it using these particle accelerators. Now, in reality, it is possible to convert materials into gold as represented in this experiment. But to the chagrin of the alchemists, they've discovered that it's much, much easier to convert gold into lead, kind of going the opposite way, taking a precious metal into a base metal. And so, kind of going in the opposite direction. And so alchemists, yes, they had kind of an alternative view of the world. but it made sense based on the information they had available, and they continued to refine their view based on what they learned. Again, this concept that these early alchemists like Robert Boyle and Isaac Newton were applying very early aspects of the scientific method in their approach of searching for, like the philosopher's stone. So to take a look at this in kind of a more recent scientific example, we tend to look at the field of taxonomy. The field of taxonomy is focused on categorizing organisms and so that we can understand them and communicate them. And so this is an article came out in The Guardian in January of 2022, identifying 224 new species in the greater Mekong region in Southeast Asia, including Vietnam, Cambodia, Laos, Thailand, and Myanmar. These new organisms, these new species, were discovered in 2020. And, we've got a monkey here. We've got, take a look at the notes here. We got a newt over here. So they're new species. But how do we describe them? How do we understand what it is they're doing? Do we have to start from scratch every time we discover a new species and try to characterize it? With these concepts of taxonomy, we've got a system where we can say that, this monkey, even though it's a new species, it probably has some similarities to other types of monkeys. This newt over here, again, another species, but, it may have some similarities to other types of newts that are present. Distinct differences because it is a unique species, but there's some similarities that we don't have to start studying this from scratch. And so taking a look at the historical kind of development of the field of taxonomy, kind of the father of taxonomy is recognized as Linnaeus over here. And he basically kind of attempted to describe how we can categorize the different organisms and the different kind of creatures, the different things that we can see in the world around us. Now, Linnaeus was highly religious. He actually was attributed a quote, whether or not it's true or not is subject to interpretation, but Discrepit Linnaeus Disposivit basically said God created, but Linnaeus is organized. And so the goal of Linnaeus was to come up with a way in which he could categorize and group together organisms that were similar to one another. And so he came up with this taxonomical structure, starting out here very, very broad in this concept of kingdoms, and getting more and more inclusive, more and more exclusive, so identifying specific characteristics that are present that would include within this group, but would exclude others, ultimately to the point of getting into the species level here, where you've got a very unique kind of set of organisms. And so even though Linnaeus started out, with a kind of questionable viewpoint, questionable basis for all this, he created the binomial nomenclature using the genus and species, so like humans, Homo sapiens, that's used today. Now, Linnaeus organized this into a two-kingdom system, and a quote attributed to him basically says, natural bodies are divided into three kingdoms of nature: the mineral, the vegetable, and the animal. Minerals grow, and so if you take a look at crystallization that's occurring, you can see minerals growing. Plants, which are capable of growing and living, and then animals that grow, live, and have feelings. And so based on those characteristics, he categorized those things that he saw around him. While later, maybe 100 years later, Haeckel, under the influence of Darwin and this concept of evolutionary relationships, kind of tried to, again, categorize the living organisms. And we're focusing in on the living organisms now, setting aside minerals, which we now know aren't truly alive, but were included in Linnaeus's kind of scheme of describing all things. But Haeckel, again, studying these evolutionary relationships, felt that there were going to be four kingdoms. And so basically what they were going to be are the animals and the plants, which were consistent with what Linnaeus had identified, but he also felt that they were protists, kind of this middle kind of stream in here. Make sure I've got it right. And then Monaria, very simple organisms here. Now Haeckel was a scientist studying protists, so he gave protists a very kind of prominent realm with his kingdom system. But these are kind of very simple organisms that kind of don't fit into the category of animals or plants. Now, if we apply this this information further, coming now into the 20th century, we've got Robert Whittaker here in the late 1960s, kind of organizing, the same living organisms, but different criteria, different ways of categorizing them. And he basically, again, kind of similar to Haeckel, he's got animals over here. Animals over here. I'm on the wrong screen. Plants over here on this side. He's got the protists, and then he's got the Monera, kind of simple organisms here. But then he added in the group of fungi. So fungi including like yeasts and mushrooms. And so this five kingdom system made sense based on the criteria that he used. Whittaker basically said that our Monera down here are going to be bacteria, simple single-celled organisms that are really kind of basic. We've got animals. Find the animals over here. Animals are going to be complicated, kind of generally multicellular organisms. They got more than one cell being present, and they obtain their nutrients through the process of ingestion. Plants over here on the other side, again, often, generally multicellular, many cells forming up their structure. They're going to obtain their nutrients by the process of photosynthesis. And then what separated the fungi here in the middle were that these are organisms that receive their nutrients through the process of absorption. So a fungus, a mushroom, will grow out on dead and decaying material and absorb the nutrients from that. He, again, included Haeckel's protist category in here, and protists were basically kind of more complicated than the Monera, the bacteria down here, but they're not a plant, they're not a fungus, they're not an animal, so kind of a catch-all of other groups of organisms. To take this a step further, Carl Woese, in the mid to late 1970s, started looking at RNA sequences, so starting to look at this concept that we can study not just the appearance, not just the characteristics of organisms, but their actual genetic makeup. And in doing that, by studying RNA, he was able to show that the bacteria over here that were very primitive were very, very different than these archaea here. These archaea bacteria are, kind of strange creatures, often in very extreme environments. But they're distinctly different from our simple bacteria over here. And reality, even though they remain single-celled organisms, they're organisms that are comprised of one cell, they're closer to the plants and animals and protists and fungi than what was previously thought. So again, the same organisms studied in slightly different ways and understood and applied in using different systems into these different levels of categorization. And so if we take a look at this, starting over here with Linnaeus, with animals and plants, going here to Haeckel's, basically the same organisms, but they're being distributed differently. Going to the five kingdom system of Whittaker, or the six kingdom system over here. Again, we're just fine-tuning that process. So similar to the way that alchemy came up with a very simple explanation of the world around them, and then it's revised. It's changed over a period of time. They corrected those things that were wrong and adopted those things that are right, generally through the process of the scientific method adopted by Boyle and Newton, who were, acclaimed alchemists. So take a look at an example beyond that. Taxonomy, does it apply to kind of the everyday world? Taking a look at how we can describe the solar system and where the Earth is in relationship. The kind of very early model was this geocentric model. Geocentric basically meaning that the Earth is going to be at the center of the solar system, the center of reality in essence. And then everything around us, these other planets, are going to be in circular orbits kind of around the Earth. And this was put forth predominantly by Ptolemy, a Greek philosopher, and again, great model. It described a lot about what was going on, in the celestial bodies, the stars and the planets, and the moons kind of moving around. But it had some problems. If all of these things are in a circular orbit around the moon, I'm sorry, not around the moon, around the Earth, why is it that Mercury and Venus always seem to be near the sun? Why is it that during periods of time it appears as if some of these planets are moving backwards in something that's called retrograde motion? And so the Ptolemaic version of the solar system was modified with the addition of these little epicycles, these kind of small, kind of circular kind of orbits. Kind of as they would be moving around, they would be kind of doing these circular kind of corrections to account for differences in the actual observations that are being made. Now, the Ptolemaic view of the solar system lasted for a long period of time because it answered most of the questions that people had. But later on in the 1500s, better tools, better telescopes, better ways of studying the heavens and applying mathematical models. Copernicus developed a heliocentric model of the solar system. And so in this heliocentric model, the sun is at the center of the solar system. Still maintain the circular orbits, but in this case, the planets are going to be orbiting around the sun. Now, this again was better than the Ptolemaic model, but it still had some problems. It still maintained circular orbits over time. An astronomer named Kepler added elliptical orbits, so they're not perfectly circles, they're kind of squished, so they're kind of like almost like little ovals. And so they're kind of going kind of longer in one direction than in the other. Galileo, using telescopes that were available at the time, was able to look at the larger moons of Jupiter and see that they weren't kind of orbiting around the sun or orbiting around, other structures. It was actually orbiting around the moon. And so this idea that we could have these objects within the solar system that aren't following this very simple model of everything in orbits around the sun. And then finally, Isaac Newton, the same Isaac Newton that I described earlier as an alchemist, came up with the laws of gravity, which allowed then to come up with a better explanation of planetary movement. So again, different model based on different ways of studying the world around us. But as we can see, scientific progress sometimes challenges societal norms, and that's something we see even today. And so proponents of the Copernican model of the universe ran into challenges. Over here, we've got Galileo. Galileo was accused of heresy for claiming that Earth was not at the center. Again, kind of religious leaders at the time felt that the prominence of the Bible, the prominence of religion, and the view that God created Earth and God created man as the kind of paramount structure and the paramount organism within at least the solar system, if not the universe. If the solar system doesn't orbit around man and Earth, then perhaps man isn't as special as people had thought. Maybe things aren't as cut and dried as what was thought about there. And so, Galileo was charged with heresy, was actually sentenced by 7 out of the 10 inquisitors, but a little bit connected. So he was sentenced to house arrest. But over here we've got Giordano Bruno, another Copernican who was highly religious, who was actually executed for the beliefs. And so even though a lot of claims that he was executed for just simply supporting the view of the Copernican universe, where we had this orbiting around the sun rather than the Earth, the actual documents associated with it was this idea that Bruno was advocating for exoplanets, planets beyond the Earth, which again challenged the religious tenets at the time, because if there are other planets and life of other planets, what does that mean about man's prominence and God's view of man? And so again, challenges to society based on scientific progress. And this continues today. And so we've got situations now, we're still kind of in the midst of the COVID-19 pandemic. We need to have an ability to share scientific information very, very rapidly. And so over a period of time, and this actually began before the COVID-19 pandemic, was this idea that scientists could share preprints of their information. So information, papers, in essence, that they've researched and written that would normally go through kind of a peer review process and not be seen until they'd been vetted, until other scientists had looked at them, had kind of critiqued them. Does it seem to be accurate? Are there problems with it that need to be corrected? And that's a process that occurs kind of hidden in the field of science. By adding in these preprints, we have the advantage of getting the information out there much more rapidly, but it's not vetted information. It's not information that's gone through the process of peer review, and so there could be problems with it. And so the disadvantages of this is that there may be errors that are caught in the peer review process that are corrected. It's valuable to have the information, but it's more valuable to have accurate information. And so the major preprint servers, medRxiv is an example of them. They basically have this disclaimer on it and saying that preprints are preliminary reports of work that have not been certified by peer review. They should not be relied on to guide clinical practice or health-related behavior and should not be reported in news media as established information. So even though we've got this disclaimer on this, as we've seen in the COVID-19 pandemic and a lot of the scientific claims that have come out with this, sometimes the information isn't as accurate, and sometimes the information is changing rapidly, which contributes to this kind of confusion about what's going on. And so because of this, and this is studied prominently within COVID-19, and we're only 2 years into it, a little over 2 years into it, so there's a lot more that needs to be understood. And there are concerns that the use of these preprints can contribute to misinformation. And so just an example for studies that have been published relatively recently, the NASCO study in 2021 looked at about 5,000 preprints that were posted from January through the end of May 2020, and saw that only a small proportion of those articles that were posted on these preprint servers had been published. It was only about a little under 6%. And so that the majority of the other articles, even though they'd been put out there, even though many of the journals were accelerating the acceptance of COVID-19 related information in publishing them, these were, 93% of the papers were not being published. And so taking a look at the difference between the preprints that were published versus the ones that were not, those that were published tend to have higher citation counts, and those that were just in the preprints tended to have a much, much lower scientific impact. And so the question is, are those articles, those preprints that were put out there that were not published, are they potentially of lower quality that may not have made it through the peer review process? The Kadvanch paper over here took a look at this idea, again, that they were publishing these articles much more rapidly to get the information out there, but basically came to the understanding that the number of retractions, papers that had been pulled from publication because there were problems with the study of some type, or expressions of corrections or concerns were much, much higher for COVID-19 articles that had gone through this accelerated process than for non-COVID-19 related articles. Again, indicating that in the rush to publish some of this information and get the information out there on the preprint servers, sometimes it may not have been as high a quality as people would have liked. Two papers by Teixeira da Silva basically, kind of raising the concern over here that putting these preprint servers on PubMed, the kind of National Library of Congress, National Library of Medicine, and the National Institutes of Health, primary database for biomedical research, if these preprints are listed and indexed in the main biomedical database, does that add additional status that they haven't kind of earned up until that point? And then finally, the last article over here raises the concern that many times these preprints kind of disappear. All of a sudden, they're not there. And there's question that these preprints have been withdrawn for some reason, but they're not quite sure why. Normally, if a paper is retracted or pulled from publication because there are concerns about it, there's a notice. It actually has a watermark that goes across it. It doesn't go away forever. It is basically republished with a watermark that says retracted on it and an explanation for why it's been retracted. If we're taking a look at the situation where these preprints are just disappearing, is it because there were errors in them? Is it because there were problems with it? Is it because they weren't necessarily supporting the evidence that they were trying to claim? And so potentially, great that we can get this rapid information out there through the use of preprints, but we need to look at it with a little bit of a skeptical eye. And as we've seen over the last 2 years, that skeptical eye hasn't always been present. And so this gives rise then to this question. We know that science ideally should be an objective and self-correcting process of inquiry where scientists go through and look at what has been published and expand on what has been published and hopefully kind of corrects the record going forward. But oftentimes that's not necessarily the case because we end up with kind of incorrect information that stays out there. Science as a self-correcting process isn't ideal. And if we use the scientific method and the scientific process properly, it should be a self-correcting process. But our scientists are human. I'm human, scientists are human, you're all human. And so we're imperfect. We have potential biases. We have a certain amount of stubbornness that we don't want to admit when we're wrong. We can have mistakes, unintentional mistakes in the way we did the experiment and the ways we did controls that have limited the value of the study that we're happy about, that we feel good about. But others looking at it from an outside view may pick up on the problems that we've got. Ego, do we want to kind of admit that we made mistakes? So like our view of alchemy, and that kind of go back to the beginning. This history of alchemy is that we made some mistakes early on based on the information that was available. But science has progressed beyond that. Science, through the experimental method, has gone through and applied, almost like this self-correction, has applied this process to have a better understanding about the world around us. It isn't perfect. Science will continue to make mistakes. But over time, with scientific progress, with this kind of hopefully impartial, objective use of the scientific method, we're going to gain the knowledge and a better understanding about what's going on in the world around us. And this gives rise to the scientific or ethical dilemma in science, this question. As scientific research continues to refine our understanding of the world, as we learn new information, COVID-19 was completely unheard of. But like that view of taxonomy, it had certain COVID-19, the virus behind COVID-19, SARS-CoV-2, is similar to other other coronaviruses. So we didn't have to start from scratch, but it is distinct. And so some of that early information was proven or was shown to be wrong. And so as more experiments, as more understanding of the COVID-19 virus came out, our viewpoint of what was going on changed because we became more informed about what's going on. And so the ethical dilemma science question is, in an era of fake news and alternative facts, how do we ensure that current, high quality, and accurate scientific information is available, accessible, and used? How do we ensure that information that has been retracted, information that is simply gone away on these preprint servers, is not being used as the basis for arguments for a decision or arguments, to move a position forward as we go forward in time. Especially as we saw with the Copernican view of the universe, especially when the scientific knowledge and understanding runs against societal norms, against kind of cultural viewpoints, and as we've seen in COVID-19, against political perspectives. And so how do we ensure that we are using good quality science as we are going forward? And so that finishes up this overview. Hopefully you can see how I kind of tied in alchemy with this scientific progress. I'll link in some of the articles below that we used in references in this. Again, some information about the preprints, those 4 articles that I had there. So thank you. Hopefully you enjoyed this, and we'll be posting another one soon. Thank you, and have a great day.